test 1, okay, you do the chapter 2, 3, and 4. Chapter 2 is regarding rectilinear, chapter 3 is regarding the curvilinear motion, and chapter 4 is relative motion, okay, which is that covered in your test 1. Okay, so for your chapter 2, 3, and 4, you do the analysis on the particles, okay. On that particles, there is no dimension, okay, because we can see that for the particles, okay, you have no dimension, but we just consider if the particle has the weight, then we will consider it has a weight lah, but not the dimension. Okay, but for the rigid bodies, we will need to consider the dimension. If you apply the force to these rigid bodies, then you will have a moment or a rotation. Okay, a rotation from the rigid bodies because we consider the dimension. Okay, so for the rigid body also, you need to do the analysis of linear, curvilinear, and relative motion analysis. Okay, so what is meant by rigid bodies? So rigids means that if we apply the force to the body, so the body is not change the shape. Okay, the shape of the rigid body is not change. That's why we call as a rigid. Okay. So, why do you need to learn this chapter 8 is that to design a machine or mechanism to perform the desired motion. So, in a rigid body system, so you need to know how to calculate the motion of the body. Okay, this is the example of the oil rig. Okay, how to dig the oil from the earth. Okay, so if you notice that there is a lot of motion by the mechanism of the systems. Okay, if you look at this schematic diagram, okay, you may notice that at this part it will move up and down, and on this part, okay, there is a rotation occur at this center of rotation. Okay, at this part here, you will notice that there is a rotation by the arm, okay, and from the motors as well. So it's a combination of motion in the system. So you need to learn to determine which member or which rigid bodies has a translation motion, rotation motion, and also a general plane motion. So basically, in a one system of the machine, you will have this kind of motion lah. Okay, basically you have three type of motion. The first and the second one is we call this as a simple motion. Okay, it's a simple motion, and the third one is we can say that it's a complex motion lah. Okay, basically translation include rectilinear and curvilinear rotation, and also the second one is rotation. Okay. All right. So in these topics, we investigates the relationship between the velocities and acceleration. Okay, of various point forming a rigid body during a motions. Okay, motion analysis of this point will still be based on principle used in the kinematics of particle. Okay, which is the rectilinear, curvilinear, and relative motion analysis. Okay, you need to remember all the knowledge that you learn from chapter 2, 3, and 4 and apply it to this rigid bodies analysis. Okay, so basically for this chapter, we focus on two-dimensional motion, okay, just X and Y. A particular rigid body can move in one of this type of motion. So basically you have three type of motion: translation, rotation, and general plane motion. So what is a general plane motion? General plane motion is a combination of translation and rotation. Okay. All right, for this type of motion, velocity and acceleration will be made. So basically, in this chapters, you have two parts. The first part is regarding the velocity analysis, and the second part is regarding the acceleration analysis. So, if I'm not mistaken, for your test two, this topic will cover two questions. The first one is velocity analysis. The second one is the acceleration analysis, if I'm not mistaken. Okay. Alright, so this is the example uh, how to recognize the type of motion by the rigid bodies. Okay, alright. So what is translation? Translation means that no rotation of any line in the body. Okay, no rotation. Motion of the body is specified by motion of any point in the body. So we use the point in the rigid bodies to specify either the rigid body move in translation or not. Okay, for example, we have A is a rectilinear translation. Okay, so in this rigid body, we choose 2 points here, point A and point B. So the first position move to the second position. All right, if you notice that point A and point B move to A prime and B prime, and you may notice that the motion of point A and B is on a straight line. It's a straight line motion. Okay, it's a straight line, and the distance covered by point A to A prime and point B to B prime is the same. Okay, the distance here is the same. The displacement here is the same from A to A prime, from B to B prime, and then we can see that the path is parallel. A and B, the path is parallel. Okay, so we can consider that this is a translation motion, a rectilinear translation. If you have a point C here, point C to C prime, okay, the path is on the straight line, and then the distance covered from C to C prime is the same as A to A prime and B to B prime. So if you have this kind of uh, system, then this we call it as a rectilinear translation. Okay. So the example of the real world application is rocket on the test leg. Okay, because it's moved on a straight or rectilinear translation. Okay, so the second one you have another translation, but then this is a curvilinear translation. Okay, the difference between rectilinear and curvilinear, the path of the point of the rigid body from the first position to the second position is in a curved path. Okay, from point A to A prime, from B to B prime is a curved path. Okay, but and the distance covered by A to A prime and B to B prime is the same. Okay, let's say I put here as 2 meter, and then B to B prime also 2 meter. The distance covered by all the points in the rigid body is the same. If I have C to C prime, the distance covered also 2 meter. D to D prime, the distance covered also 2 meter. But the difference between rectilinear and curvilinear, the curve path, the path that point travel from position 1 to position 2 is on a curve path. Okay, so basically, for the curvilinear translation, the application is parallel link swinging plate. So basically, it's a swinging condition. Okay, it's based on a swinging condition. Let's say I have a point A here and point B. So this plate is swing. Okay, from the left to the right, from the right to the left. Okay, means that the path of this point A is like this. You may notice that this is the path that being traveled by point A, and also this is the path that been traveled by point B. Okay, if let's say A travel to A prime, B travel to B prime, the distance covered here is the same as B to B prime. Okay, so this is a swinging condition. Swinging condition means that it's not for this plate, it's not rotating about a fixed axis lah. Okay, it's just swings. Okay, the point on this plate, because we focus on this plate. Okay, the point on this plate just swing. Okay, it's not rotate. Okay, it's just swing with respect to these both arms lah. Okay. Alright, so for another motion is a fixed axis rotation. Okay, means that you will have a center of rotation, and the another point is rotates about that center of rotation. So for example, you have this rigid body. So A is your center of rotation, okay, and B is rotating about A. Okay, if this system is in motion, you may notice that only the point B is moving. Point A is fixed. Okay, point A is fixed and point B is moving about point A. Okay, so for this case, we know that this system is moved with a rotation. Okay, is moved with a rotation motion. Alright, so for the rotation, all particles move in a circular path at the axis of rotation. All lines perpendicular to the axis of rotation rotate through the same angle. Let's say you have a point C here, so C move to C prime, so the angle also the same. Okay, the angle covered from C to C prime is the same, B to B prime is the same. But for this rotation, you may have a fixed axis or the center of rotation. For the curvilinear translation, for this plate, you don't have a center of rotation. Okay, there is a difference between curvilinear and rotation. Rotation, you need to have one fixed center of rotation, and this center of rotation is not moving. Okay, all right. So for the third one is a complex motion, which is a general plane motion. Okay, we can say that the general plane motion is a combination of translation and rotation. So if you look at this example, from point A move to A prime, and from B to move to B prime, we can see that the distance covered by point A to A prime and B to B prime is not the same. It's different. Okay, this is due to the combination of translation and rotation. So during the analysis, you need to know which member move in translation, which member move in rotation, and which member move in general plane motion, because different type of motion will have different type of analysis. Okay, so if you notice that the example here, we have a connecting rod in a reciprocating engine. So let's say this is the rod. Okay, this is the rod that we want to do the analysis. Okay, okay, if I draw the rod here, okay, let's say I have 2 points. So here is point A, here is point B. Okay, this point A is affected by this arm. Okay, and this arm is rotating. Okay, means that if I calculate the velocity of this point is respect to this angular velocity. So the direction of this point might be to this direction. Okay, and then for this point B is will affected by this block. Okay, this block can move to the left or to the right only. Okay, so the line of action for this B to this direction, so it might be to this to the right. Okay, let's say I assume to the right, and then this one is to this direction downward. Okay, if you notice that the direction of the velocity here is not parallel. Okay, so it's in different direction. So from this case, we know that, and also for this rod, it's not rotating. There is no center of rotation for rod AB. And also the velocity line is not parallel. So we can say that this is a general plane motion. Okay, for the translation, the direction of velocity should be the same for every point in the body. For the rotation, it should have a center of rotation. But for the general plane motion, you may notice that there is a combination. Okay, and usually the direction of velocity is not parallel or is not parallel. Okay, in order to determine okay the rigid body is moved with general plane motion. Okay, so far any question? Ada soalan tak? Okay, so this is the first analysis that you need to do for this chapter. The first analysis is you need to know how to determine the type of motion. Okay, so this is rectilinear translation, move in parallel straight line of the same distance. Okay, so you may notice that if from okay, so this L rod is moving to this direction. Okay, upward the inclined plane. So if this whole rigid body move to this direction, you may notice that the velocity at B, velocity at A, and velocity at C will be the same. And all the velocity are in parallel, in a straight line parallel. Okay, so we can say that for this kind of system is a rectilinear translation. Okay, so that's why the velocity of the body, okay, of every point on the body will be the same lah. Okay, so same goes to this distance. Okay, so if you differentiate displacement, then you will get velocity, and if you differentiate velocity, then you get acceleration lah. Okay, so like I mentioned previously, the displacement for each point in the rigid body from position 1 to position 2 will be the same. So if you differentiate the displacement, then you will get the velocity lah. Same velocity for each point in the body. Okay, so since the body is not rotating, then you will have no angle, obviously. Okay, because your rigid body just move in a straight line. Okay, so if you have no angle, then you will have no angular velocity, then you have no angular acceleration. So this is angular velocity, means that the velocity due to the rotation, and then this is the angular acceleration. Okay, okay, so the direction of acceleration is the same as velocity if the system is accelerating. If your system is decelerating, then the direction of A will be opposite to V. So basically this is just the same things lah, uh, like particle. Okay, kinematics of particle. Okay, for the curvilinear translation, okay, you may notice that the same things, all the point move in parallel curve of the same distance. Okay, usually for the swinging component. For this case, we have a rod here, the swinging component of a rod. Okay, so for this case, the most important part here is AB is equal to CD, meaning that the arm here should have the same length. This arm AB and this arm CD should have the same length in order to produce the curvilinear translation. If AB and CD don't have the same length, then this curvilinear translation cannot occur lah. Okay, it can be occur if AB is equal to CD. Okay, so if you notice that you have a 3 point here, point B, point B, point E, and this point D. And then this point B is swinging B1 to B2 to B3. E1 is swinging E1, E2 to E3. D1 is swinging to D2 and D3. So this is the parts covered by this point. You may notice that the parts here is parallel. Okay, and the distance covered by B to B3, E to E3, D to D3 is the same distance. Okay, it's just swings from D to D3, from position 1 to position 3 with the same distance. So we can say that for this rod, okay, it's moved with curvilinear translation. So I just focus on this rod. Okay, for this arm is a different story lah. For this arm, it is actually rotating. For this arm A, B, and C, D, the focus here is on EBD. Okay, we focus on the L rod, the rigid body that I colored with the red line. Okay, I just focus with EBD. So this EBD is actually moving with curvilinear translation. Okay, so the velocity on the EBD here will have the same velocity lah for every point in the EBD. Okay, in the EBD member, the velocity is the same. Okay, VB1 equal to VD1 equal to VE1, VB2 equal to VD2 equal to VE2. Okay, same goes to the position 3. Okay, since the velocity is the same, then the acceleration will also be the same lah. Okay, because the acceleration is derived from the velocity. Alright, so since curvilinear is not in a rotating motion, so you don't have the angular velocity and you don't have also the angular acceleration. So both value should be equal to 0 lah. Okay, so this is a curvilinear translation. Okay, so the focus here is on EBD. For AB and CD is a different story lah. Okay. Alright, so we go on the another rotation, which is a fixed axis rotation motion. Okay, so you may not ask this in this example. You have the arm that is a pivot fixed at point A, and point B is rotating about point A. Okay, point B is rotating about point A. So from this case, we know that this is the rotation motion lah. Point B, this rigid body AB is moving with rotation motion. Okay, so since your rigid body is moving with rotation motion, then you have the angle lah. Let's say from B to this position B prime. So you have the angle here. If you have the angle, then you will have the angular velocity, and also you will have the angular acceleration lah. Okay, because your rigid body is moving with rotation. So angular acceleration is V is equal to R omega. So omega is equal to V over R. So this is the equation for the angular velocity. Okay. Alright. So what is R? R is the radius of from the distance from the point. Let's say from the point B to the center of rotation. So this is a center of rotation. So this R is calculated from the center of rotation to the point that we want to calculate lah, the velocity. Okay. So okay, so let's have a look to this body A, B, C, D, E. Okay, you have this body here, A, B, C, D, E. Okay, please remember on one rigid body, you will have only one angular acceleration. Okay, so for this whole rigid body here, you have only one angular acceleration. Okay, please remember that. Okay, for one whole rigid body, you will have only one angular acceleration. Okay, so in order to calculate the VB here, all right, so V, okay, you have here is angular velocity is equal to V over R. Okay, so means that you can calculate V is equal to R omega. So this V and R should be perpendicular. Okay, V and R should be perpendicular. Okay, let's say I want to calculate the velocity at point B. Okay, so perpendicular to the R is this line. Okay, this is the line that perpendicular to this distance R. Let's say I put here as R RA, RAB. Okay, A to B. So perpendicular to this RAB is your velocity. Okay, since the omega is the angular velocity is rotating clockwise direction, so I know that my V should this direction lah, because this A, this whole system is rotating clockwise direction, so the V should follow the omega. So this is my VB. Okay, so this VB should be perpendicular to the R, or you can determine that V is tangent to the curve of the point B. So this is the path of the point B. Okay, the path of the point. Let's say for this one, the path of motion. Okay, so V should be tangent to the path of motion lah. Okay, let's say at this point B, V should be tangent to the path of motion or and 90 degree to this radius. Okay, this is your VB. Okay, so if your rigid body is moving with rotation, you will have the same angular velocity for all point in the rigid body, but the velocity, the V will be different. Okay, the V will be different. The omega is the same for the whole system, but the V for each point will be different. Okay, because you have V is equal to R omega. Omega will be the same for all points, but R is different. Okay, the distance from the center of rotation to the point on each point on the rigid body will be different lah. Okay, let's say if we want to calculate VB. Okay, VB is equal to omega dot with RB or time with RB. So this is the distance of RB. Alright. And then let's say you want to calculate VC. So VC is here. So VC is this direction, perpendicular to this R. Okay. So time with this one is RC. So omega time with RC. So RC and RB is different. So that's why velocity at point C is different with velocity at point B due to this radius or due to this distance from the fixed center of rotation. Okay, same goes to point D. Point D is affected by this distance, which is RD, and the V should perpendicular to RD or tangent to the path of motion. Okay, and E, this is E, VE, and then this is your RE. Okay, so uh, this is why the velocity of each point on the rigid body will be different due to the R. Okay, due to the R. All right, so there is one more thing here. The velocity or the translation velocity, which is V, for the center of rotation VA will be 0. Why? A is the center of rotation and you don't have a distance. RA is equal to 0. Okay, so basically A is a fixed, we call it as a fixed center of rotation. Fixed means that it's not in motion. So for VA, so A cannot move. So that's why VA is equal to 0 lah. Okay, so you have the velocity at point B, C, E, and D. Okay, so no translation motion for the axis of rotation point. So basically this one is for point A lah, point A. Okay, you don't have a no translation motion for point A. Okay, because this V represent the translation velocity, omega represent the angular velocity. Okay, any questions so far? Ada soalan tak?
No, sir.
Okay. So this one is fixed axis rotation. Okay, so then we go on. Okay, take note that for a body moving in a rotational motion, there must be a center of rotation. All points on the rigid body rotate about the same center of rotation, means that if we can refer to this figure, point D, point E, point B, C, E, D is rotating about A. Okay, each point on this rigid body is rotating about the same point. Okay, so omega angular velocity is the same for all points on the rotating rigid body. Okay, means that all points for the whole rigid body, you will have only one omega lah, only one angular velocity. Velocity of a point is perpendicular to its radius line, pointing toward the direction of motion and tangent to the path of the motion. Okay, so this is how you determine the velocity of each point in the rigid body when the rigid body move with rotation motion. Okay, velocity of a point is larger when the point is further away from the center of rotation and vice versa. Because V is equal to R omega. Omega is the same for all points. If R is higher, then your V will be higher. Okay. Velocity of a point always zero at the center of rotation, which means that the translational velocity lah. Okay, which is the V. Okay, velocity of a point is linear velocity. Straight line velocity and not equal to angular velocity. So V is a linear velocity, all right? Omega is angular velocity. Okay, you will have omega for the rigid body that move with rotation. Okay, so this is different things lah. A is linear acceleration. Alpha is angular acceleration. All right. So A here is related to this V, linear, and linear angular is related to this angular velocity. Okay. Alright, so this is the difference between curvilinear and rotation. Okay, so in figure A, you have a curvilinear translation, figure B is rotation. So if you notice that we focus on this plate, okay, we focus only on this plate, A, B, C, D. Okay, we focus on the plate A, B, C, D. So you may notice that for this case, point A, point B, point C, and point D, okay, is rotating on the parallel path. So this is the path by point A, the path by point C, and the path by point B and point D. You may notice that the distance covered by each point A, B, C, D is the same from position 1 to position 2. Okay, the dashed line here represent the position 1 and then it's moved to position 2. Okay, so the distance covered is the same. Okay, to make the rectangular plate move with curvilinear, this arm here should have the same distance as this arm. Okay, if the arm is different length, then you have a different story lah. Okay, the velocity of point, let's say you have different arm, okay, different length of arm. B and A, the path of motion will be different lah. So you will have no curvilinear rotation, curvilinear motion for this rectangular plate. But if you have the same length of arm, then this point A, B, C, D will move with curvilinear translation. Okay. Okay, so for the rotation, we have the same rectangular plate, but we fix at the center, one center of rotation, which is point O. Okay, you may notice that all point A, B, C, D, okay, will rotating about O. So this is RB, this is RA, this is RC, and then this is RD. So all the point is rotating about the same fixed axis line. Okay, so for this case, we know that the system is rotating. Okay, is rotating. Okay, so if you can notice that C1 to C2, the path from C1 to C2, D1 to D2 is different with the path of A1, A2, B1, AB2. The distance covered is different. Okay, by A to A2, B1 to B2, C1 to C2, D1 and to D2. Okay, and it has a fixed axis of rotation. So this is the difference lah. Okay, how to determine either the system move with curvilinear or rotation. Okay, so this is example 8.1. Determine the velocity of point B, okay, and C. Okay, you have the omega here equal to 2 radian per second. Okay, one more thing, your omega should be the unit should be in radian per second. If you are given with RPM, then you need to change to radian per second. Okay, so you have angular velocity is rotating clockwise. So basically, we know that this is the distance, the radius line, RAB. This is the radius line, RAC. Okay, so since since the omega is moved clockwise, so basically we know that velocity should be this direction lah. VB perpendicular to the radius VB, right? And the path here, the path of motion will be like this lah, because it's rotating. Okay, this is the path of motion. Tangent to the path and 90 degree to the radius line is your VB. And then for the C, this is the line of the line of motion, the line of VB, the line of velocity lah. Okay, not the line of motion, but the line of velocity. Okay, since the omega is rotating clockwise, so basically I know that this should be my VB, my VC. So 90 degree to the radius. And if I draw the path, so the path will look like this lah, the path of motion. Okay, it's moved with rotation path. Okay, so this V should be perpendicular to the radius and tangent to the path of motion. Okay, so V is equal to R omega. So VB is equal to RAB omega ABC. Why I put ABC? This omega represent the whole rigid body lah. Each point on this rigid body will have the same omega. So VC is equal to RAC times with omega ABC. Okay. So you know that the omega is provided, which is 0.4. Okay, 0.4. So for the omega, for this VB is equal to RAB, is that you can obtain here RAB 0.4 times with omega AB is 2 radian per second, then you get 0.8 meter per second. Okay. Okay. So for RAC is equal to 0.4 over sine 30 times with 2 radian per second, then you will get m meter per second for VC. Okay, you have angle here 30 degree, then you have the length here, then you can get this value lah. Okay, sine 30 is equal to RAC over 0.4 over RAC. Then RAC is equal to sine 0.4 over sine 30. Okay, so this is how lah. I hope everyone know lah. This one this is the right angle triangle equation. Okay, sine equal to opposite of hypotenuse, cos is adjacent of hypotenuse. So this is how to determine the length of RAC. Okay. Okay, so this one is example 8.2, determines the velocity of points B, D, and E. Okay, so B, D, and E Okay, and then you will have AB equal to CD, meaning that the arm AB and CD has the same length, and then the angle here is 30 degree. Okay, so we know that this BDE will move with curvilinear translation. Okay, so uh, okay, let's see if I draw this L rod here. So B, D, and E. So I need this one is B, this one is D, this one is E. Okay, so I need to determine VB, VD, VE. Okay, so I know that this BD and E move with curvilinear translation. Okay, curvilinear translation. Okay, and due to this curvilinear translation, VB equal to VD equal to VE. Okay, how to determine the this V, the velocity on member BDE? So I need to use the arm. I need to use the arm information. So I have the information from the arm, which is omega AB, 4 radian per second. Okay, because this arm is actually rotating. Arm AB is rotating. Arm CD also is rotating. Okay, and both arms have the same length. Okay, for BDE is affected by the rotation motion of AB and CD. Okay, the motion of B, D, and E is affected by the motion of AB and CD, and AB and CD is actually rotating. Okay, in order to determine the velocity of B, D, and E, so we need to use the information from this omega AB. Okay, so we know that point B here is located at the point B is located on member AB, and point B also located on member BDE. Okay, and this member AB is rotating, is moving with rotation. Okay, this member BDE is curvilinear. All right, so meaning that we know we can get the value of velocity at B. Okay, since we know that member AB is rotation. So basically, if I draw the member, this one is A, this one is B. So provided in the question omega AB is equal to 4 radian per second. So I know that the path of motion should be like this lah, because it's rotation. Okay, it should be like this. This is the path of motion of point B. Okay, so point B will have the linear velocity that is perpendicular to this radius and tangent to the path of motion. So this is VB, 90 degree from the radius and tangent to the path of motion. So this is path of motion. Okay, so this VB here can be calculated. V is equal to R omega. So VB is equal to RAB times with omega AB. RAB, we know that distance A to B is 0.2. 0.2 times with omega AB 4. Then you get 0.8 meter per second. Then you know that VB is 0.8 meter per second. Okay. So you know that this is your VB. Okay, provided here is the angle. The angle here is 30 degree. So the angle here should be 30 degree lah. Okay, so from this member AB, I know the VB. I can get VB. So this point B also located on member BDE. Alright. So meaning that from here, I can say that this is your VB 30 degree with the value is 0.8 meter per second. Since I know that BDE is moving with curvilinear translation, so a velocity on each point on the body will have the same direction and the same magnitude. Okay, same direction and the same magnitude. So same things, 30 degree, VD is equal to 0.8 meter per second. Okay, the same thing here, 30 degree, I have VA equal to 0.8 meter per second. Okay, so if I get, since from this member BDE, I know that VB equal to VE equal to VD. Okay, because it's moving with curvilinear translation. So from this VE, I can obtain the omega here lah. Omega, this one is D, sorry. This one is D, this one is E. Okay, from this VD is equal to RCD dot with omega CD. So VD is 0.8, RCD is what? 0.2 dot with omega CD. Omega CD is equal to 4 radian per second. So basically, since AB and CD have the same length, then the omega is the same lah. Omega AB is equal to omega CD. Okay, any questions so far? Ada soalan tak?
No, sir.
No, sir. Okay. So before we move to this slide, I think we take a break for 5 minutes. Okay. Okay, guys. So let's have a look to another motion, which is a general plane motion. Okay. So for the general plane motion is we can say that if you notice your rigid body, okay, does not move in translation motion or rotation about a fixed axis motion, meaning that it's moved with general plane motion. Another way to put this is a rigid body has 2 points or more that is moving in different type of motion in non-parallel direction. So non-parallel direction. Then the rigid body is said to be moving with general plane motion. Okay. So usually we can use the direction of the velocity. Okay, let's say this point here is moved due to the rotation by this arm. Okay, means that this should be this velocity lah. So this is the R, and 90 degree to the R, and this is your V. Let's say I put here as point A, VA. And then this point here is moving due to this block. This block can only move with translation, okay, from to the right or to the left. Okay, so let's say it's moved to the right. So this is point B, VB. So you notice that VB and VA is not in parallel lah. It's not in parallel direction. So we can see that the rod AB, this rod is actually moving with general plane motion, or usually I put as GPM lah, general plane motion. Okay, if your rigid body move with rotation, okay, you can use V is equal to R omega to determine this V. Okay, so sometimes for this AB, okay, for this rigid body that move with general plane motion, you cannot use the V. You cannot use the, let's say for this point A, okay, you can use this I move this one. Okay. For this point A here, you can determine the V. If you have this omega, then you can determine the V lah. For this point A, you can determine VA. But for this point, VB, how to determine this? How to determine this velocity? If the velocity of the if the velocity of the block is not provided, okay, how to determine this VB? Okay, but with the information that you have here is VA. Okay, this VA can be obtained from this omega, but then how to determine this VB? Okay, in order to determine this VB, you have two methods for velocity. For velocity analysis of a general plane motion, you have two methods. The first one is instantaneous center of zero velocity and relative velocity. Relative velocity is the same things that you do as chapter 4. Okay, you do the analysis on the chapter 4 is the same thing. So the new analysis that you will learn is instantaneous center of zero velocity. So this instantaneous center of zero velocity only applicable for velocity lah, because as I mentioned previously, you have two analysis. The first one is velocity, the second one is acceleration. Okay, for this method is only applicable for velocity. It's not applicable for acceleration. Okay, as the name given here is instantaneous center of zero velocity. Okay, as mentioned here, using relative motion is valid for both relative velocity and relative acceleration. Using instantaneous center of zero velocity is only valid for velocity. So this is the note, okay, the important notes here. All right, okay. All right, so here is to determine okay. All right, so I think that's it for the information from the general plane motion. Okay, first we need to determine the type of motion of the rigid body. Okay, we do some exercise to determine the type of motion of the rigid body. So let's say I have the rigid body AB. Okay, so at point A, the path of motion is this line. The velocity line. Sorry, the velocity line is this line. Okay, and the velocity line of B is this line. And it's been provided in the question, VB is to the right. Okay, horizontally to the right. And if I pull this member AB to the right at point B, then at point A, it will move VA is this direction. So VA and VB is not parallel. So I know that member AB is moving with general plane motion. Okay. So for this one is the first one and the second one. So member AB, okay, what type of motion of member AB? For the second figure, anyone?
Rotation.
Rotation. Okay, member CD, what the type of motion? Anyone?
General plane motion.
CD, member CD, C and D.
Rotation 2.
Yes, rotation. Because member CD, you have the fixed axis rotation here at D. Member AB also you have fixed axis of rotation at A. Okay, what would be for the type of motion for BC?
Rectilinear.
BC is rectilinear. Okay, why rectilinear?
Move up and down.
Okay, so for the rectilinear, if we go back to the This one. Rectilinear, okay, is move with all the point in the rigid body will move on the same distance lah, A to A prime, B to B prime, and also will have the same velocity line, parallel line of velocity. Okay, so for this case, since we have the axis, the center of rotation, we know that B here is rotating about A, C here is rotating about D. Okay, let's say if I draw member AB, so this one is A, this one is B. Okay, I have omega clockwise direction. So from this omega, I can determine the velocity, the linear velocity. So I have here is my R, AB. So since AB is rotating, so this is my path of motion lah, path of motion. Okay, path of motion is something like that. Okay, in a circular path. Okay, so perpendicular to the R and tangent to the path is your VB. Okay, so this is from member AB. B is affected by the motion of member AB. Okay, so I know this is my velocity line of point B. Okay, let's move to member CD. So member CD, all right. All right, so member CD. Okay, let's say I assume that the omega of CD is this direction lah. I assume omega CD. All right, so you can assume either this direction or this direction is the same things. Okay, it's not a problem. What we want to know is that it's just the velocity line. Where is the velocity line of C? Okay, this one is C, this one is D. Okay, so this one is the radius RCD. So RCD. So point C is rotating about point D. So the path of motion, okay, this is the path of motion, okay, circular path of a member of the point C. Okay, so let's assume that omega CD is counterclockwise. So basically, this would be your VC lah, VC 90 degree to the RCD and tangent to the path. Okay, you may notice that this is my VB, this is my VC. So I draw my member BC. So this is my member BC. Okay, this is B, this is C. B, C. So VB is affected by the rotation of the rod AB. So downward, VB. And then I have here is VC is affected by the rotation of member CD. So here I have the certain angle. So here at a certain angle VC. Okay, so you may notice that the velocity line of VB and VC is not parallel. Okay, so from this case, I know that BC is actually moving with general plane motion. Okay, so for member BC is general plane motion. Okay, so let's say you want to assume that omega CD is outward, let's say. So then your VC is outward. So it's not an issue lah. So this will be your VC. Okay, you still notice that VC and VB is not parallel. Okay, it's a different direction. Okay, any question so far? Ada soalan tak? Okay, so let's have a look to another exercise. So this is exercise figure 3. Okay, what would be the what would be the motion of AB?
Rotation.
Rotation. BC,
PM.
BPM, CD, rotation.
Rotation.
Okay. So this importance lah. The first thing you need to determine uh, the motion of the member. Okay. So if you have a rotation, then you can know that directly V equal to R omega. Okay, if you have a GPM, then you have another analysis lah, either relative velocity or relative motion or instantaneous center of zero velocity. Okay. Alright, so we go on this figure 4. Okay, what would be AB? AB obviously is rotation. CD is rotation. BCE is what? What is the motion of BCE?
GPM.
GPM. What is the motion of EF?
GPM.
GPM. The motion of F?
Rectilinear.
Yes, rectilinear translation, TR. Okay. So for EF, you may notice that for this BCE, okay, for this point B, it will move the linear velocity is affected by the rotation motion AB. Okay, since the omega is outward, so we know that this is VB lah. Okay, and for the point C, this is the velocity line. Okay, perpendicular to the radius. So either this direction or this direction. So you know that VB and this VC will have different direction. So PCE is actually the GPM. So same goes for E. Okay, so for E, in order to determine this velocity line of E, okay, you need to, for this case, I will discuss later lah. Okay, how to determine this VE. Okay, how to determine this VE. Okay, you need to use the instantaneous center of zero velocity. So basically from here we know that this is let's say I want to assume VF. Okay, and VE will rotate, will move not parallel to this VF. Okay, so that's why EF is GPM. F, the block is rectilinear translation. Okay, so for this case, AB is rotation. C is rectilinear translation. And then for BC is actually GPM lah. If I draw BC, it will look like this. Okay, at point B, this is VB. At point C, this is VC. Okay, this is the line of velocity lah, either upward or downward. Okay, you may notice that VB and VC is not parallel. So that's why BC is a GPM. Okay, general plane motion. Okay. Okay, we have another example. This one is this one figure what 4, 5, 6, 6. Okay, what is the motion of BCE?
Curvilinear.
BCE.
Curvilinear.
Yes, BCE is a curvilinear motion. Alright, curvilinear is TC. Okay, curvilinear translation. Okay, so AB is equal to CD is what? Is rotation. Okay, CF, what would be the motion of CF?
General plane motion.
CF general plane motion. F is
Rectilinear.
rectilinear, rectilinear translation. Okay. Right. So we go on the 7th figure. What would be the DC?
GPM.
DC GPM. CDE?
Curvilinear.
CDE.
GPM, I think.
Why GPM? If this member is rotating,
Fixed axis.
yes, fixed axis is rotating at D. If is more in motion, you will notice that point E and C will rotate lah. So rotation. AB also rotation. Okay. So we go on number 8. You have the you can say that it's a roller. Okay, it's rotating. This roller is rotating and moving to the right. What would be the motion for this rigid body?
Rotation.
This the whole rigid body moving to the right. It's just like your car tire. Okay, when your car is moving, you may notice that your tire is rotating, but your car is moving, let's say forward or backward.
Rectilinear.
Rectilinear. Rectilinear means that all the point moving with the same distance and with the same velocity line. Okay, let's say. Sorry?
Is it curvilinear?
Curvilinear. Curvilinear, let's say you focus on 2 points here, point A and point C. If this roller rotating, okay, what you will notice that from point C and point A. This roller is rotating and that is moving to the right. What will happen to point
GPM.
C and point A? Yes, GPM. Okay, so this we see this direction, and then your VA is this direction lah, because your VA is rotating about C. Okay, your point A is actually rotating about point C, but your point C is moving to rectilinear to the right. Okay. Okay, if you can imagine like your car tire, this is the center of your car tire, and then the point at the outside here, okay, is A, this one is C. So C is moving rectilinearly to the right, and then this A is rotating. That have a VA which is perpendicular to this R. So basically, you will notice that VA is not parallel to VC. Then this roller is actually a GPM lah, general plane motion. Okay, so this case only happen when no sliding lah, no sliding occur. Okay, means that your roller is can rotate on the surface. If this roller is sliding, means that it's not rotating. So we can say that point C and point A will move, VA and VC will move rectilinearly lah, rectilinear translation if sliding occur. Okay, if sliding occur. So for the no sliding occur, then means that your roller can rotate. Okay, your roller can rotate, then you will have a GPM. If there is a sliding occur, then it will become a rectilinear translation. Okay. Okay. So for the translation motion, velocity of all points are the same. Velocity means what? Means magnitude and direction. These two things should be the same lah, not just the magnitude. Direction also need to be the same. Direction, magnitude of all points are the same for the translation motion. Okay. So for the rotation about a fixed axis, then you have V is equal to omega R or R omega. So V should be in meter per second, radius should be in meter, angular velocity should be in radian per second lah. Okay. And then please remember, one rigid body or member will have only one omega lah. Okay, one rigid body or member will only has one omega. Okay, let's say you have this shape. Okay, and this is a one member, then you will have one omega. Okay, let's say for this case, you have member AB. This member AB will have omega AB, and then this member, so BCE is not in a rotation. So this one will have omega CD. This one will have omega CF lah. So each member will have their own omega, one member. Okay. If like this, the whole member is a one member here, then you have a one omega. Okay, so just remember, one rigid body or one member will have only one omega. Okay, so basically for the analysis of general plane motion, okay, the analysis of general plane motion, we know that the velocity of each point is different. The direction is different also. So what we can say that it's actually a combination, translation and rotation. Okay, let's say you want to focus that on point A. So means that translation with A plus with rotation about A. Okay. So from this case, we know that if it's translation with A, if you pull the rigid body upward, point B also will tend to move due to this VA lah. So that's why you have VA. But at the same time, point B will tend to move on the another direction that cause a rotation about point A. Okay, due to this difference in velocity line, that it will tend to cause a rotation. Okay, so that's why here you may notice that point B will tend to rotate about point A. Okay, so that's why we can say that point B tend to rotate about point A. It's just like relative motion analysis. Okay, the motion of point B, VB stroke VA. Okay, so since we have here we have three vectors. Okay, so VB is equal to VA plus VB stroke A lah. So this is the same thing like I mentioned previously, VB is equal to VB minus VA. So we use the positive form. Okay, the positive form is VB is equal to VA plus VB stroke A. Okay, so vector VA plus with vector VB stroke A equal to VB. Okay, so VA plus with VB stroke A equal to VB. Okay, so this is the relative analysis lah for the system that are moving with general plane motion. Okay, so you need to use this analysis. The first analysis is relative motion lah. Okay. Okay, let's say we go on the second one. You have this plane motion. If you focus on the rod AB, okay, rod AB. So at point A, this is the velocity line. At point B, this is the velocity line. So different velocities lah for point A and point B. Okay, so if you want to choose its translation with A, so means that point B tend to move seems like velocity A. At the same time, point B here is moving downward, so it will cause a rotation at point A. Okay, it will cause a rotation about point A. So means that since we fix point rotation about point A, so meaning this point B is rotating with respect to point A, VB stroke E. Okay, VB stroke E. Plane motion equal to translation plus rotation. Okay, so then you can get this kind of analysis lah. Then you can draw the triangle. Okay, so basically it's not fixed. Okay, either it's translation with A plus rotation with A. Basically you can choose another point. For this case, you want to choose point B, meaning that plane motion equal to translation with B, meaning that point A tend to move the same velocity as B for the first one, and plus with, since point A is moving to this direction, so it will tend to rotate about point B. So you fix point B, so meaning that point A will rotate about point B. Point A will rotate about point B. Okay, so your equation will looks like this. VA minus VB. VB is equal to VA VB plus VA. This one is VA. Okay, so you can form the triangle and you can calculate lah. You can calculate the velocity A and B as well for this rigid body. Okay, like I mentioned previously, sometime you can for this for this for this part I mentioned previously. Okay, you have VA. Okay, this VA can be determined from this from the rotation of this arm. And then how to determine this VB? And then you need to use this relative analysis lah. Okay, you use this relative analysis to determine this VB. Okay, basically if you use this equation, okay, if you choose point A or point B, you will get the same answer lah. Okay, let's say here you use a translation with B and rotation with B. The answer is still the same if you use a translation with A or rotation about A. It's the same things lah. Okay. Okay, so for the triangle, you can use trigonometry, or you can use a rectangular method lah, rectangular. Okay, rectangular method, you need to resolve into X and Y direction. Okay, if a trigonometry, then you need to use a sine, cosine and sine rule lah. Okay, to determine this, to determine the magnitude. Alright, so this is another analysis. Okay, another analysis. This is regarding the relative motion. Okay, instead of relative motion, then you can use the method called as instantaneous center of zero velocity, or in short form, we call as ICZV. Okay, instantaneous center of zero velocity. Okay. Okay, how to determine this instantaneous center of zero velocity? So this is represent the C here. Okay, so the first one, okay, let's say we focus on the rod AB. Okay, rod A and B. Okay, so on each point AB, you will have in the velocity of each point, VA to the right, VB downwards. Okay, to find this instantaneous center of zero velocity, you need to draw the perpendicular line to velocity for each point. Okay, let's say this is my VB. I draw a perpendicular line to VB. And then for this VA, I draw a perpendicular line to VA. The intersection point here is called as instantaneous center of zero velocity. Okay, at this center, then you will have the omega. Okay, at this point where the plane is rotating. Okay, the center of rotation will have a zero linear velocity lah. Okay, that's why we call as instantaneous center of zero velocity, because this is the center. Okay, but you have the omega. Okay, at this point, at this center, at this instant of the center here, the rod AB is rotating about omega AB. Okay, then you have omega AB here. Alright, so you can relate this VB and VA with this omega AB. Okay, so you know that this is the radius B. Okay, perpendicular to this velocity. So VB is equal to RAB omega AB. Okay, and then at this line here is your RA. So VA is equal to RA omega AB. Okay, so if you know VB, then you can determine lah what is the angular velocity of this rod AB. Okay, what is the angular velocity of this rod AB? Okay, so this is the second method, which is you still can determine this VB and VA by using the omega AB, the omega of the rod. So this omega is at the point of the instantaneous center of zero velocity lah. Okay, so for this one, you notice that omega AB is equal to VB over BC. BC is here. This one is AC. The same things lah. Okay. Alright. So you will learn more on how to do the analysis lah. Okay. Okay. From the question, from the exercise, then you may notice that how to use this equation for the instantaneous center of zero velocity and the relative motion. Okay, basically it's still the same. You get the same answer. Okay, it depends on you which method that you want to use. Okay. Okay, so now I will go on this exercise. So to determine the instantaneous center of zero velocity of the following rigid body. Okay, so I see ZV only for general plane motion. Okay, only for the body that are moving with general plane motion, then you will have the instantaneous center zero of velocity lah. Center of zero velocity. Okay, let's say for point A, this is the line of velocity. So this is the line of velocity to the right. So basically the velocity here downward. So if I draw the perpendicular line to VA, so this is the perpendicular line to VA, and then this is perpendicular line to VB. So the intersection here is your ICZV. Okay, so this is the direction of VA, this is the direction of VB. So I know that this is my omega AB lah. Okay. Okay, so I go the second one. Previously I know that this is my VB. Okay, and then this is my VC. Okay, if I draw the perpendicular line to VC and VB, so VB, this is perpendicular line, and then this is VC, perpendicular line. So the intersection point here is your ICZV. Okay, if this is the direction of VB to VC, then I know that this is my omega lah, omega BC. Okay, because remember BC is GPM, general plane motion. Okay, any questions so far? Okay, I go to the second one. Okay, so for this figure 3, where is the instantaneous center of zero velocity for BC? Because previously we know that BC is GPM. Okay, where is the uh, ICZV for this BC? Anyone? Where do you think the center of zero velocity?
C and D.
Sorry?
C and D.
C and D? Okay. So for the instantaneous center of zero velocity, we need to focus on the rigid body that are moving with general plane motion. Okay, why do we need to determine this ICZV? Because we need to know this omega, because we know that for the rigid body that are moving with general plane motion is a translation plus with rotation. So if the rigid body move with rotation, then you should have a omega. Okay, so for this case, for the relative analysis here, you can determine the omega AB based on this VAB lah, based on this velocity is root B, then you can determine the omega AB. Okay, for relative motion. But for the instantaneous center of zero velocity, first you need to determine the center of zero velocity, and then from that center you can determine the omega. Okay, based on the radius from the velocity to the center of zero velocity. Okay, so for this case, we have BC here. BC is actually moving with general plane motion. So I know that this is my point BC, VB, and then this is my VC at a certain angle lah, 90 degree to the radius here. Okay, so if I draw a perpendicular line to, okay, if I draw here, B and C. So previously we determined the velocity line, okay, in order to know the motion of the member. So from the previous example, from the previous exercise, we know that this is VB, this is VC. The velocity is different. That's why BC is general plane motion. So if I draw the perpendicular line from both velocity, from VB, this is my perpendicular line to velocity. And then for VC, this is my perpendicular line. So where is this intersection point?
Point C.
Yes. So for this case, point C is actually your ICZV, instantaneous center of zero velocity at point C. So at this center, you will notice that VC is actually equal to 0 lah. Okay, at the center of rotation, your linear velocity will become 0 lah. Okay, so we will look into that lah on when we do the analysis after this. Okay, so we go on. Okay, so if you notice that from the previous example, your center can be outside from the rigid body. For this case, the center is here, which is outside the rigid body. For the BC here, the center is also outside the rigid body. Okay, for the third example here, you may notice that the center of zero velocity is on the point on that rigid body. Okay, okay, that's why it depends on the situation lah. Okay, let's say we know that BC here, BC, the fourth figure here, this one is moving here, VB, and then here is moving VC at a certain angle. So if you draw perpendicular line to each velocity, you will notice that the center lies on point C. So this is perpendicular to VC. Perpendicular line to VC. So you may notice that the ICZV is actually on the point C. So it can on the rigid body, or it can be on the outside of the rigid body for the instantaneous center of zero velocity. Okay. All right. So for this case here, previously, if we look at the previous analysis that we do, we know that this is the things lah. AB is equal to R, CD is equal to R. So we have BCE and EF. So basically, this is GPM. So it should have ICZV, and also here you should have ICZV. Okay, for the rigid body that are moved with general plane motion. Okay. Okay, so we know that BCE. Okay, this is B, this is C, this is E, and B, C, E. Then we will have EF lah. EF, the member that are moved with general plane motion. Okay. So we know that F, this is the line of velocity, either upward or downward is up to you. So let's say I just choose where is the direction lah? Downward lah. Okay, I choose downward. Okay, it's not an issue for the direction. Okay, as long as you know the velocity line. Okay, so E, I don't know. Okay, I don't know where is the velocity line of E. Okay, then we go first on B. So B, I know that is affected by the rotation of this rod. So there is omega AB here. So basically, this is the direction lah. Okay, for point B is VB upward. So VB. Okay, so for point C is affected by the rotation of this rod lah. Okay, so this is my radius. So perpendicular to the radius is the velocity lah, VC. Okay, so perpendicular. So either to the right or to the left. It is up to you lah. So I choose to the left lah, VC. Okay, VE, I don't know. But in order to draw the instantaneous center of zero velocity, we just need two points only. So if I draw a perpendicular line to VB, and I draw a perpendicular line to VC. Okay. Then I will get instantaneous of zero velocity for ICZV for BC. Okay, because I connect 2 points here, B and C. So this one is IBC lah. I put here as IBC. Okay. Sorry. This one is instantaneous center of zero velocity for BCE. Okay. This one is for BCE. So omega that I obtain here is omega BCE. Alright. So now I can determine the velocity line of E based on this center of rotation, based on this ICZV that I draw here. Okay, so I know that this is my perpendicular line here. So basically, if I put RB here, so VB is equal to RB time with omega BCE. Okay, so VC here, this is the length RC. So VC is equal to RC time with omega BCE. Okay, so VE is this distance RE from the center of zero velocity. So VE is equal to RE time with omega BCE. So this is my radius. So I know that VE should perpendicular to RE. Okay, R and V should be perpendicular. So perpendicular to this R is actually your velocity line lah. So this is your velocity line for E, either upward or downward, perpendicular. Okay, so basically I want to choose downward. Okay, so this is my VE. Okay, so okay then I put my VE on the member EF. Okay, so this is my velocity line of VE, and then this is my velocity line of VF lah. So since EF also moving with general plane motion, then I need to I need to determine this general perpendicular line lah to velocity. So perpendicular. So basically the intersection here is IC ZV for member EF. Okay, any question? Ada soalan tak?
No, sir.
Okay, so I hope you can try on this part lah. Okay, so you just need to determine which member that are moving with general plane motion. So basically CF lah, the general plane motion. So then from CF you need to determine this you need to determine the ICZV lah. So basically this is the VF. So this should be might be here for VC. Okay, so you draw perpendicular line to each velocity. Okay, then you can get the ICZV. Okay, the center of zero velocity. So same goes for this one. You know that here is your GPM. Then you need to determine your ICZV for the member that are moving with GPM. Okay, same goes for this one. Alright. Okay, so there is actually a special case for this. Okay, so I think I will finish until this special case first. Okay, for the ICZV, there is a special case where you for the case one, point I or center of zero velocity does not exist. Okay, does not exist. Okay, for this case, if you notice that B and C, if we do the analysis, we will notice that B for the system that are moving with a general plane motion, if I do on okay, let's say for this case here, this is your VB and then this is your VC. So VC and VB is not parallel. Okay, that's why this one is a GPM lah. But there is another case like this where you will notice that at this instant, VB and VC is parallel. At the instant here, VB and VC is parallel. So for this case, at this instant, VB is equal to VC and then omega BC is equal to 0. So VB is equal to VC is like a rectilinear translation lah. Okay, for this case. So for this case, your instantaneous zero velocity is not exist. Okay, because VB and VC is parallel. So if you draw a perpendicular line for each velocity, you will not get the intersection point. Okay. All right. So then we go on the second figure. So if I mentioned previously, for the system that are moving with curvilinear translation, the arm here should be the same length. Okay, if the arm here is on different length, then you will have a general plane motion lah for your let's say for this L rod. Okay, for the arm that have the same length, then you will have a curvilinear translation. But there is a case where you have a different length Okay, different length, and you don't have a instantaneous center of zero velocity for this case. For this case, BC is actually GPM. Okay, but for this instant, okay, pada waktu ini, for this instant, the velocity is parallel. Okay, the velocity here is parallel. Okay, if this system move a little bit to the right, then your VB is not equal to VC. But for this instant, for this particular instant, your VB is equal to VC, even though your BC is in general plane motion. At a certain condition, at a certain location, there is exists where your VB is equal to VC, means that if you draw the perpendicular line, you will not get the center of zero velocity. Okay, at this particular instant, we can treat this BC as a rectilinear translation, where your VB is equal to VC and omega is equal to 0 lah, because it's rectilinear. Okay, there is no rotation. Okay, this is the special case lah, special case for instantaneous center of zero velocity, where you will notice that you will not get the ICZV. Okay, and another special case is where your point I is coincide with a point. Okay, like we do previously. For this case, your I is located at point C. Okay, your if your I located at point C, then your VC is equal to 0 lah. For the center of rotation, the linear velocity will become 0. Okay. And then for this case, you will notice that the instantaneous center velocity is located at point B. So VB is equal to 0. Okay, same goes for this case. Okay, where your I here, instantaneous center of zero velocity, is located at the point inside the member. So VC is equal to 0. Okay, usually the instantaneous center of zero velocity is located outside the rigid body lah, usually. But in some case, it can located inside. Okay, coincide with a point. Okay, so on the case number 3, okay, point I from okay, this is the case number 3. So basically, this is a very rare case lah. Okay, case yang jarang berlaku. Okay, you have the same direction of V, but you have a different magnitudes lah, VA and VB. Okay, for this case, the same direction, different magnitude. Basically, you can determine the instantaneous center of zero velocity. Okay, so for this roller lah. Okay, so since even though the direction is the same, but the magnitude is different. So the magnitude is different, causing this roller to become GPM lah. Okay, if this roller become GPM, then you can determine the instantaneous center of zero velocity. Okay, so for VA is have a higher length for the velocity because a higher magnitude, and VB shorter length due to the less magnitude here. Then from the tips of the velocity line here, then you can determine the instantaneous center of zero velocity. Okay, basically this is a very rare case lah. Okay, so if you have a opposite direction, for this roller, is also become a GPM. Okay, okay, so from the tip of the velocity, okay, the intersection point can be the instantaneous center of zero velocity. Okay, you just connect the perpendicular line to the velocity, and then with the tips line of the velocity. So you draw the perpendicular line first, and then from the tips, the connection, the intersection here is your ICZV lah. Okay, so this is the case number 3. Okay. So, and then case number 4 is a rolling without slipping. Means that you have a friction, not smooth. So basically your roller can rotate. Okay, can roll in this floor. So if your roller can roll in this floor, then you will at the point A you will have a VA at a certain angle, and VC will be moving rectilinearly to the right. Okay, so basically VC and VA will have a not a non-parallel direction. Okay, non-parallel line of action. So this roller will have a I lah, because this roller is GPM. So you can determine the I by drawing a perpendicular line to the velocity. So you draw the line perpendicular to velocity, VC, and perpendicular to VA. Then the intersection point here is actually your I, or instantaneous center of zero velocity. Okay, why do we need to determine this I? Because this I will act as a center of rotation. Okay, it will act as a center of rotation. Then from this center of rotation, then you will get the omega. So from this omega, you can relate with V is equal to R omega. So R is what? R is the distance from the point, okay, point to the, for this case, if to the I lah, to the center of zero velocity. Okay, for the case of instantaneous center of zero velocity. Okay. All right. So on the next class, we will do this example for this 8.6. Okay. So I think that's all for today. Before I end the class, do you have any question?